Hello everyone, my name is Aditya. I'm role number 1. Today I'll be presenting about the topic Android OS architecture. In this video, I'll first explain the theoretical concept of Android OS architecture. Then I'll move to the practical demonstration in Android Studio where I will show how these layers are connected to real-world Android application through a simple example. Diagram here shows the various layers of Android OS. The first layer being the application layer. Then comes the application frameworks, then libraries, which also contains the Android runtime, and then the Linux kernel at the bottom. Now, we are going to talk about the topmost layer of Android OS architecture, the application layer. It runs on the Android runtime using application framework services. Its components include pre-installed apps like contacts, phone, messages, and browsers, or user-installed apps which are downloaded from the Play Store. System apps like settings, calendar, and camera are also included in the application layer. Most of the application layer apps are written in Java or Kotlin. They run in sandboxes for security purposes. Each app has a unique user ID and runs its own processes. They usually interact with the system via application framework APIs. Each app runs in a own sandbox, which they are isolated for security. This will ensure that each app will not interfere with other apps, and each of them have their own user IDs. Now we're going to talk about the second layer, which is application framework layer. It's a core layer which provides tools and services for developers. It enables access to device features like hardware, display, and resources. Components include Activity Manager, which manages the app lifecycles, View System, which allows us to view the UI components, Notification Manager to handle alerts in the status bar, Content Providers to enable data sharing between apps. Resource Manager helps access layouts, images, and streaks. Location Manager, where GPS and network-based location services are provided. For example, like if we are using a map app, the GPS is used to track our locations. There's a location manager in this layer which does all this work. The third layer consists of native libraries and Android runtime. The native libraries written in C or C++ handle tasks like graphics, rendering, database operation, while Android runtime ensures the app run effectively. The native libraries consider SQLite, OpenGL for 3D and 2D graphics, WebKit for web browser engine, SSL for secure socket layer, and Media Framework for audio video playback. The Android runtime ensures that the app runs effectively. The Android runtime uses an ahead of time compiler which will convert Java or Kotlin code to native bytecode so that when the app runs, it boosts the speed and saves the battery life. Now we are going to talk about the fourth layer of Android OS architecture, the Linux kernel. It's the heart of the Android architecture. It provides abstraction between hardware and upper layers. Its responsibility include process management like CPU scheduling, multitasking, memory management like RAM allocation, virtual memory, device drivers like communication with hardware, security, networking, power management. Linux kernel is the foundation of Android, making core operations like process scheduling, memory, and hardware communication. Like when you take a photo, the camera driver in the kernel communicates with the camera hardware, while the power management optimizes battery usage. Here, in the main activity XML file, I've used the linear layout as the root element. The orientation is set to vertical, which means all the UI components are placed one below the other. I've also given the padding and centered elements so that it stays neat and aligned. Now, I've specified 4 buttons here along with their IDs. Now, these IDs will be used in the Kotlin file to connect the layout with the code. Here, I've specified a text view to display the result when a button is clicked. For example, when I click the application layer, the text view will show the details of that layer. I have set the text size to 16 SP and added padding and center so that text is readable. The XML file defines the structure of our app's UI. It contains 4 buttons for each Android OS layer and one text view to show the output. In the next video, I'll explain the Kotlin code that powers the logic behind these buttons. We're going to look at the Kotlin code in our main activity Kotlin file. This is where we write the logic to make the app more interactive. Here I've imported the necessary packages to handle the code. We start with the main activity, which extends app compact activity. Inside the class, I've declared variables for text view and 4 formal buttons.
In the onCreate method, I set the layout for activity using set content view. Then I connect each variable to its following XML using the find view by ID. This allows the Kotlin code to control the UI components from the layout. Now, set the application layer button. When I use this button, the text view updates the display information about the application layer, which includes apps like Contacts, Phone, and other apps installed from the Play Store. So the framework layer, it displays device details such as model, manufacturer, and Android version. This is done using the build class, which is part of the application framework. For the HL layer button, is used to check if the GPS is enabled. This demonstrates how the frameworks communicates with HAL, which then interacts with hardware like GPS. For the kernel layer button, it displays the Linux kernel version. The kernel is the foundation of Android OS and then drivers process management. So the Kotlin code connects to your XML layout with logic. Each button represents a different Android OS layer, and when clicked, it updates the text view details in that layer. Now we're going to run the app in the emulator and see the practical demonstration of it. Now, first let's click the application layer. This is the topmost layer of Android. In our demo, pressing the button shows how apps are isolated and communicate with the system using the framework. Now, when we click the framework layer button, it displays the model, manufacturer, and Android version. This information comes from the Android build class, which is part of the application framework. It shows how the framework provides ready-made APIs for developers so we don't have to directly interact with hardware. Instead, we can call the framework methods. Now, when I click the HAL layer button, it shows whether the GPS service is enabled or disabled using the location manager. Demonstrate the framework how it interacts with hardware abstraction layer and talks to the actual GPS hardware to the drivers managed by Linux kernel. So when you press this button, it shows how Android apps directly use hardware features via HAL. Now, when I click the kernel layer button, it shows how the kernel layer version running on the device. The kernel is the heart of OS. It manages CPU, drivers, and processors. By deploying the kernel version, we can see the foundation on which the Android OS is built.
Now we're going to talk about the benefits of the Android OS architecture. The Android OS architecture provides several benefits. It improves maintainability, quality, robustness of apps. Since the architecture is scalable, it supports more users and new features as the app grows. Testing becomes easier and bugs can be identified and fixed quickly thanks to the layered structure. Security is also improved through sandboxing and permissions. Most importantly, hardware independence ensures that apps can run on a wide variety of devices from budget phones to high end systems. Now, we're going to talk about the challenges of Android OS architecture. The biggest issue is fragmentation. The Android runs on thousands of devices with different screens, sizes, hardware, and OS versions. Developers often have to test across multiple devices to ensure compatibility. Security is another concern because the open ecosystem allows apps from outside the Play Store, which increases the risk of malware. Battery and performance issues are also common, especially when apps are not optimized and keep running in the background. Updates are another problem. Unlike iOS, Android updates are rolled out at different times depending upon the manufacturer and the carrier. So many users often remain on outdated versions. Finally, the learning curve is steep since beginners need to understand multiple layers, APIs, and frameworks before they can build advanced apps. In the future, Android OS will be deeply shaped by artificial intelligence. The first major trend is on device artificial intelligence and machine learning using TensorFlow Lite. Instead of depending on cloud servers, AI models can directly run on smartphones. This makes apps faster, more secure, and even usable offline. Good example is Google Translate's instant camera translation feature. Next, we have voice assistants and natural language processing. Android already integrates with Google Assistant, but developers can build custom natural language processing models for their own apps. This means you can see more voice driven apps and conversational AI experiences in the future. Personalization is another area. AI will power apps that adapt to user behavior. For example, YouTube recommendation, personalized shopping apps, and customized learning platforms. Computer vision is enabling augmented reality and virtual reality on Android devices. Using AR Core, apps can lay virtual objects in the real world, like AR furniture shopping or AR navigation in Google Maps. In healthcare, vision based Android app can assist in diagnostic. Then there's predictive analysis. AI models can anticipate what the user might need, like suggesting replies, predicting battery usage, or providing next step recommendations in finance or healthcare. The future trend is AI driven app development itself. AI tools are starting to generate code, automate testing, even suggest UI designs. That means in the coming years, AI will not only run inside apps, but also help in building those apps faster and more efficient. Now, we are going to summarize what we have seen today. We have discussed about the various layers of Android OS architecture, including applications, application frameworks, libraries, Android runtime, and the Linux kernel. We have also seen the practical application using Android Studio. We have discussed critical concepts like how layered abstractions enables hardware independence, security process isolations, performance optimization through native execution, and modular design, and how it supports ecosystem diversity.